This is SpaceTime Series 25, Episode 105. Coming up on SpaceTime, the surface of the planet Mercury undergoing rapid change, why it never pays to bet against Albert Einstein, and solving the missing galactic carbon monoxide mystery. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study has found that the surface of the planet Mercury is changing rapidly. The findings, reported in the journal Geophysical Research Letters, suggest that a mysterious, little-understood geological process is underway beneath the surface of the planet nearest the Sun. Astronomers have long estimated the age of a terrestrial body's surface by the number of impact craters it has. The more craters, the more asteroids must have hit, and consequently the older the surface must be. But scientists have long believed that the rate of asteroid impacts has been steadily decreasing with time. Still, age estimates for virtually every surface other than the Earth rely on this cratering rate. But as more asteroids hit the surface of terrestrial bodies, that means there are less and less available for future impacts. So consequently, the rate of impacts must be decreasing with time. Scientists also believe the cratering rate varies with distance from the Sun. And all these variables combine to be most poorly constrained for the planet Mercury, whose position near the Sun has made the acquisition of high-resolution imagery rather challenging. That's where NASA's Mercury Surface Science Environment Geochemistry and Ranging spacecraft, or MESSENGER, comes in. MESSENGER orbited Mercury between 2011 and 2015, providing the best images to date of the tiny planet, which is about the same size as Earth's moon, and takes just 88 days to complete each orbit around the Sun. The observations by MESSENGER had a spatial resolution down to just 5 meters, thereby allowing quite detailed images. Now, scientists trying to improve the cratering rate estimate for Mercury have been using these images as part of their calculations. Astronomers examined 58,552 pairs of MESSENGER images which had overlapping surface coverage. These act like sort of before and after shots, showing any new craters which may have formed. By painstakingly comparing these before and after images, astronomers identified surface changes and computed the implied yearly rate of change per square kilometre. Overall, the authors identified 20 new features in their dataset. Of those, 19 are quasi-circular structures, with diameters between 400 metres and 1.9 kilometres, and one of them was surrounded by radial rays typical of impact craters on Mercury. Now, 19 new impact craters on Mercury in 4 years of MESSENGER images implies a cratering rate for small impactors that's 1,000 times greater than the current accepted value. The authors have rejected such an extreme revision of cratering rates. 1,000 times greater is just too big a hurdle to jump, and have instead begun advancing an alternative hypothesis. They claim that many of these features represent what they describe as endogenic geological changes. You see, there is a characteristic small-scale Mercury surface formation. It's a sort of hollow, a rounded depression, but without a sharp crater-like rim. Mercury hollows have previously been observed to occur mainly in the least reflective portions of the planet's surface, as well as regions modified by large impact craters. Now, comparing their 19 features with previously mapped geological units, the authors found that 12 are in or very near low reflectance surface regions, and 6 are in the vicinity of craters with other known hollows. Now, regardless of the feature's origins, the observations show that Mercury's surface is undergoing significant evolution. Now, if the alteration rates implied by these features are consistent with the long-term average, 99% of the planet's surface could undergo change within the next 25 million years. That's the blink of an eye in geological terms. And that rate of change far exceeds what's previously been imagined for Mercury. So without a doubt, these newly observed features will likely be a key focus for the European Space Agency's Bepi-Colombo mission, which is currently on its way to the rock nearest the Sun. This is SpaceTime. Still to come, why it never pays to bet against Albert Einstein, and the missing galactic carbon monoxide mystery. All that and more still to come on SpaceTime. They say it never pays to bet against the great Albert Einstein, and that still holds true today. Back in 2019, despite the efforts of many scientists, general relativity survived its most comprehensive test near Sagittarius A star, the supermassive black hole at the centre of our galaxy. A team of scientists led by Andrea Getz from UCLA undertook the test and reported the findings in the journal Science. Her observations turned out to be totally consistent with Einstein's theory of general relativity. Getz says Einstein was right, and that means we can now absolutely rule out Newton's law of gravity. Still, Getz maintains that Einstein's theory is showing some vulnerability, mainly because it can't fully explain gravity inside a black hole. And at some point, scientists will need to move beyond Einstein's theory to a more comprehensive theory of gravity that better explains what a black hole is. Einstein's 1915 general relativity theory holds that what we perceive as a force of gravity isn't a force at all, simply the effect of mass on the curvature of space-time. It's like suspending a rubber sheet and then putting a bowling ball at its centre. The rubber sheet will naturally curve down around the bowling ball. And if you then roll a small, say, tennis ball across that sheet, it'll naturally be deflected to a lesser or greater degree depending on how close it is to the depression caused by the bowling ball. Gravity and space-time simply translate that idea into 4 dimensions. Einstein's theory is the best description we have so far of how gravity works. But the laws of physics, including gravity, should be valid everywhere in the universe, including inside a black hole. To test relativity theory the best they could, Getz and colleagues monitored a star known as SO2 in 3 dimensions as it completes its orbit around Sagittarius A star. The full orbit takes some 16 years. Black holes have such high density that nothing can escape their gravitational pull, not even light. They cannot be seen directly, but the influence on nearby stars is visible and provides a signature. Of course, once something crosses the event horizon, that's the black hole's point of no return, gravity becomes so strong that it can no longer escape, and it's doomed to fall forever into the black hole singularity. Luckily, the star SO2 is still far enough away from the event horizon that even at its closest approach, its photons aren't pulled in, and therefore will eventually be seen by telescopes on Earth, although they take some 27 million years to get here. Getz's team say their work's the most detailed study ever conducted into the supermassive black hole and Einstein's general theory of relativity. The key data in this research is the spectra where the star made its closest approach to Sagittarius A star. The spectra, which Getz describes as the rainbow of light from stars, shows the intensity of the light and other important information about the star, such as its speed to or from the observer. It also shows the star's composition. All these data were combined with measurements that Getz and a team have made over the last 24 years. The spectra and images were all collected by the giant 10-metre Keck twin telescopes atop of Mauna Kea, a dormant volcano in Hawaii. Measurements were also taken with the Gemini Observatory and the Subaru telescope, both also in Hawaii. Getz and her colleagues took their readings about every 4 nights during the most crucial periods in 2018. Seeing stars go through their complete orbit provided the first real opportunity to test fundamental physics using the motions of these stars. Having SO2's orbit in 3 dimensions allowed the authors to test general relativity and see how gravity behaves near a supermassive black hole and whether Einstein's theory is telling the full story. You see, in Newton's version of gravity, space and time are separate. They don't commingle. But under Albert Einstein's general relativity, they completely commingle. They're the same thing, and that's especially evident near a black hole. And Getz's team were able to see this commingling of space and time near Sagittarius A star. Einstein predicted that in this region close to the black hole, photons would have to do extra work. A photon's wavelength as it leaves the star depends not only on how fast the star is moving, but also on how much energy the photon expends to escape the black hole's powerful gravitational field. And that can be measured in its spectra. Because Sagittarius A star has some 4.3 million times the mass of the Sun, gravity in its vicinity is much stronger than on Earth. To maintain its orbit, SO2 moves around the black hole at a blistering speed of more than 26 million kilometers per hour during its closest approach. This is the first of many tests of general relativity which Getz's team will conduct on stars near Sagittarius A star. Among the other stars they're interested in is SO102, which has the shortest orbit of any known star around the black hole, just 11.5 years. But most of the other stars that Getz's team is studying will have orbits much longer than a human lifespan.
Black holes are deceptively simple and yet incredibly complex. A black hole is a region of space where the pull of gravity is so intense that nothing can escape it, not even light. We don't have the physics to describe what a black hole is because it leads to a paradox, a breakdown in our understanding of how the universe works. We only have 4 fundamental forces to describe how the universe works. Gravity of those 4 is probably the one that we have the most intuition for. You throw something up, it comes back down. But it's actually the least explored. Einstein really recognized that gravitational fields are equivalent to talking about space and time not being separate entities.
Einstein noticed that in certain situations, Newtonian laws of physics don't seem to hold. And that's why Einstein developed his theory of general relativity. We know that general relativity may not be a complete description of physics, and so in order to figure out where it's incomplete, you want to test it in regions that people haven't tested before. So people have tested general relativity on Earth, in the solar system, but never around a black hole that's 4 million times the mass of the Sun.
The first question I was interested in was, is there a supermassive black hole at the center of our galaxy? If you had asked me, would I still be doing this project 20-odd years later when we first started, I would have just laughed at you. I grew up hearing the word no all the time. You're a girl, you can't do it. You're a girl, there's no way you can get into MIT. There's no way you can get into Caltech. I think I developed a passion for proving people wrong. We have been able to increase the evidence for supermassive black holes by a factor of 10 million. And we have done this by watching how stars move. My favorite star, its name is SO2, and it makes its journey every 16 years. We're at this point where it's closest to the black hole and is experiencing the strongest pull of gravity. So we have this first opportunity to get a direct measurement of how Einstein's theory of general relativity works near a supermassive black hole.
Right there, so it's right now. What we've found this summer is that general relativity does actually describe the motion of the stars around the supermassive black hole.
That's a transformational change in our understanding about not only the existence of supermassive black holes, but the physics and astrophysics associated with black holes.
Andrea, to me, is a brilliant scientist. Her dedication and her persistence really has been at the heart of this project in order to have the patience and the level of detail required to do this work.
When I was young, I wanted to be the first woman on the moon, but I think at the same time, I also wanted to be a ballerina. I just became much more infatuated with the ideas rather than the physicality of moving myself. It's very poetic that we actually see the stars in motion doing this dance around the black hole. So what we want to do is we want to improve our ability to see a star like our sun at the center of the galaxy. because I think that's when we'll have the full view of how this dance really works.
This is SpaceTime. Still to come, the missing carbon monoxide mystery. And later in the science report, a new study shows that being sad and lonely really does shorten your lifespan. All that and more still to come on SpaceTime. A new study suggests that missing amounts of carbon monoxide, a key component found in protoplanetary disks, is hiding inside ice formations within planetary nurseries. The findings, reported in the journal Nature Astronomy and validated by observations using ALMA, the Atacama Large Millimeter Submillimeter Array Radio Telescope, explains why predictions about the abundance of carbon monoxide have failed to match up with actual observations. Depending on the system observed, carbon monoxide abundances are 3 to 100 times less than what they should be. And that would have huge implications for the field of astrochemistry, because carbon monoxide is essentially used to trace everything astronomers know about disks, like their mass, composition, and even temperature. So it would mean many of science's results for disks would have been biased and uncertain, because the compound isn't understood well enough. But by reworking an astrophysical model used to study clouds on exoplanets and the detailed physics for how ice forms on particles, how it nucleates and then how it condenses, astronomers found that unlike previous thinking, carbon monoxide is forming on large particles of ice, especially after 1 million years. Prior to 1 million years, gaseous carbon monoxide is abundant and detectable in the disks. The findings change how astronomers understand how ice and gas are distributed inside protoplanetary disks. Beijing has launched another 7 spy satellites, including one to replace a spacecraft hit by space junk last year. The Yunhai 103 was flown aboard a Chinese Long March 2D rocket from the Zhuquan Satellite Launch Center in northwestern China's Gobi Desert. Chinese state-run media claims the satellite will be used for detecting the atmospheric, marine and space environments, as well as disaster prevention, flood mitigation and scientific experiments. Its predecessor, the Yunhai 102, was apparently struck by space junk from a disused Zenit 2 rocket last year. Now, depending on who you believe, the Yunhai 102, which was launched in 2019, was smashed into at least 20 major pieces at an altitude of 780 kilometers during the collision, or it's still capable of adjusting its orbit despite the crash. The spent Zenit 2 rocket impactor was launched in 1996, carrying a Teslina 2 electronic spy satellite into orbit. Just 2 days after the launch of the Yunhai 103, a Long March 6 rocket carrying 3 Cheyenne experimental spy satellites was launched from the Taiyuan Satellite Launch Center in northwestern China's Shanxi province. The Cheyenne 16A, 16B and 17 are being described by Beijing as being used to provide data for land survey, urban planning and disaster prevention. 3 days later, yet another spy satellite, the Yougang 36, was launched aboard a Long March 2D rocket from the Zhaichang Satellite Launch Center in southwestern China's Sichuan province. And on the same day, Beijing launched 2 more Cheyenne experimental spy satellites, this time aboard a Kuaizhou 1A rocket, again from Taiyuan. The Cheyenne 14 is being described as conducting scientific experiments and verifying new technologies, while the Cheyenne 15 is being described as providing data in the fields of land survey, urban planning, disaster prevention and mitigation. It's standard practice for Beijing to describe spy satellites as being intended for harmless civilian commercial remote sensing services. However, inevitably, these are military spy satellites, equipped with high-resolution optical and multispectral synthetic aperture radar imagery systems or electronic signals intelligence gathering surveillance technologies. They're designed to provide continuous reconnaissance, monitoring areas of interest to Beijing as part of what Chinese President Xi Jinping describes as preparations for war. China now has an estimated 546 satellites orbiting the Earth, including over 224 Earth observation, surveillance and reconnaissance satellites, including at least 41 Go-Feng and 104 Yo-Gang spy satellites. This is Space Time. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more Space Time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.